The camera shakes, but the street itself moves in waves. Water pushes through cracks. A parked car sinks while nearby pavement rises. A building begins to lean even though its concrete frame remains mostly intact. The failure started below the street. Inside space is too small to see. Every grain of sand was carrying part of the city through a web of contacts. Then the earthquake made that web loosen, while trapped water took more and more of the load. The surface only revealed the transfer after it was already underway. This is called liquefaction, but nothing has melted. The grains remain solid. The water remains water. What changes is the structure that lets a pile of grains resist shear. For a short interval, a material that held buildings like a solid can deform with the ease of a dense fluid. That raises a sharper question than why did the ground shake? Most ground shakes during an earthquake without turning into this. Why do some blocks settle, crack and slide while nearby ground remains firm? The answer is not one magic earthquake magnitude. It is a match between sediment, water, drainage, and repeated strain. We are going to build that match from the grain scale upward. We will watch the hidden pressure climb, cross the threshold where contact forces collapse, and then fan out into sand boils, tilted buildings, broken pipes, and lateral spreading. The damage looks chaotic. The mechanism has a sequence. Once that sequence is visible, filled lagoons, old channels, deltas, and reclaimed shorelines become stored arrangements of grains and water. Imagine removing the pavement and magnifying a small block of soil. It is not a continuous slab. It is a crowd of grains touching at points and edges. The weight above passes through branching chains of contact, grain into grain, down through the layer, and eventually into stronger material below. Between those grains are voids. If the water table is low, some voids contain air. Below the water table, the voids can be filled with water. That water already has pressure, but under ordinary conditions the mineral skeleton still carries enough of the total load for the soil to resist distortion. Engineers call the grain-carried share effective stress. Total stress comes from everything above. Subtract pore water pressure, and the remainder presses grain contacts together and controls much of the soil's strength. Grain contacts matter because friction needs normal force. Push two rough surfaces together, and they resist sliding. Reduce the force squeezing them, and the same surfaces slip more easily. A sand layer can therefore lose shear resistance without crushing grains or heating them. It only needs the contact forces to shrink far enough. Uneven force chains bridge loads around voids. Repeated rearrangement changes those chains, and trapped water inherits more of their load. So solid ground is not a substance label. It is a working arrangement, grains locked by contact force, pores holding fluid, and drainage controlling how quickly pressure can escape. Earthquake shaking attacks the arrangement, not the chemistry. Liquefaction begins when the load path moves away from the grain skeleton and into the pore water. The first screen has three parts: susceptible loose sediment, connected water-filled pores, and cyclic loading strong and long enough to build excess pressure. Remove one part and the response changes. Loose packing matters because loose grains have room to find a denser arrangement. Shake a dry jar of sand, and the surface settles as grains fit together more efficiently. Underground, saturated sand tries to do something similar during repeated shear. The difference is that the pore water may not have time to move out of the shrinking void space. Saturation supplies the pressure pathway. In dry sand, air compresses and escapes relatively easily. Water is far less compressible. If a saturated layer is capped by lower permeability material, or if drainage paths are simply too long for the shaking interval, the attempted volume change is converted into a rapid rise in pore water pressure. Shaking supplies repeated shear cycles. One reversal nudges the fabric. The next reversal nudges it again. Stronger motion increases the cyclic stress, while longer motion can add more damaging cycles. That is why earthquake magnitude, distance, local wave amplification, and duration all matter, but none works as a single on-off switch by itself. Young river deposits, deltas, beaches, floodplains, and fills often combine loose sediment with shallow groundwater. Rock and clay-rich ground are different systems. This is why hazard follows buried geography. A modern street grid can cross an old tidal inlet without showing it. Houses may sit on fill placed over a former marsh. Two neighborhoods equally distant from a fault can have very different liquefaction susceptibility because one is founded on dense natural ground and the other on loose saturated fill. Start the shaking. The soil layer shears one way, then the other. Grains roll, slide, and try to reorganize. In a loose packing, their preferred rearrangement is contractive. The skeleton wants to occupy slightly less volume. But the earthquake is cycling faster than the pore water can drain away. The attempted contraction squeezes the water. Excess pore pressure rises. Because total overburden load changes little over a few shaking cycles, every increase in pore pressure is a decrease in effective stress. The grains are not suddenly lighter, they are simply carrying less of the load through solid contact. Think of it as a ratchet, rather than a single blow. A cycle disturbs the network and adds pressure. Partial rearrangement occurs. Another cycle arrives before drainage can reset the system. Depending on density and loading, pressure accumulates toward the effective overburden stress. The important quantity is the competition between generation and dissipation. Short, permeable drainage paths can limit pressure. Layer thickness, boundaries, density, and shaking still decide whether generation outruns dissipation. The danger is a pore pressure curve chasing the total stress ceiling. Near that ceiling, contact forces shrink and shear resistance collapses. The graph is the grain skeleton unloading in real time. The threshold arrives when pore pressure approaches the confining stress that had been holding the grains together. Effective stress approaches zero, at least transiently and locally. That condition is often called initial liquefaction. What happens next depends on density, drainage, layering, slope, and the loads above. Triggering is the start of the consequence, not its complete description. Total stress equals effective stress plus pore pressure. During rapid undrained shaking, pore pressure grows inside a nearly fixed total. Effective stress is the shrinking remainder that stabilizes the grain fabric. Near zero effective stress, frictional strength drops sharply. A foundation can punch downward. A buried pipe can rise because its buoyancy now matters more than the weakened soil around it. A surface crust can slide over the softened layer. The same hidden threshold therefore produces different visible failures depending on geometry and infrastructure. But real soil does not become a featureless liquid. Denser sand may try to dilate, or expand, once it is sheared far enough. That tendency can reduce pore pressure, and restore contact force during deformation. Looser contractive material can suffer larger strength loss. This is one reason the ground turn to water is memorable but scientifically incomplete. Liquefaction is patchy. Thin layers may trigger beside strong layers, while a foundation responds to the integrated behavior beneath its whole footprint. When shaking stops, pressure begins to dissipate through drainage. Effective stress returns as water escapes and grains settle into a denser arrangement. The soil may regain strength, but the geometry does not rewind. Settlement, tilting, cracks, displaced utilities, and shifted ground remain as the permanent record of a temporary loss of support. So the mechanism has two clocks. The fast clock is seconds of cyclic loading and pressure rise. The slow clock is drainage, consolidation, and repair. A threshold crossed for only moments can reorganize a city block for years. The decisive variable was not how liquid the soil looked, but how completely the grain network surrendered its load. One visible signature is a sand boil. Pressurized water finds a crack or weak path through the surface cap and carries sand upward. The eruption can leave a small cone or sheet of pale sediment around a vent. It is a plumbing connection between a liquefied layer below and the air above. Pressurized sand can inject through fractures as buried dikes and sills. The surface cone is only the outlet of that three-dimensional network. Settlement is another outcome. As excess pressure dissipates, grains move into a denser packing and the layer loses volume. If that compression is uneven, one side of a building or road can sink more than the other. Differential settlement is especially damaging because structures tolerate uniform movement better than distortion. At the same time, buried objects can move upward. A lightweight tank, manhole, or pipe that was held in place by strong soil may become buoyant relative to the weakened saturated mixture. The image seems paradoxical. Heavy buildings descend while hollow infrastructure rises. Both motions follow from the same loss of effective confinement. A stiffer surface crust can remain partly intact while the layer beneath weakens. The crust then breaks into rafts, tilts, or spreads apart. Cracks at the surface do not necessarily trace the shape of the liquefied layer directly. They show how the overlying ground accommodated movement after its support changed. These signs are not a universal checklist. Investigators combined observations with borings, penetration tests, groundwater, and shaking records to distinguish liquefaction from lookalikes. Liquefaction becomes especially destructive where the ground has somewhere to go. Beside a riverbank, harbor wall, canal, or bluff, the soil faces a free edge. A gently sloping surface also provides a downhill direction. Once a buried layer loses strength, the overlying crust can move laterally toward that opening. This is lateral spreading. The surface often breaks into coherent blocks separated by fissures. Each block may translate and rotate while riding over or deforming the weakened layer. Movement can be less than a meter, or reach several meters, enough to tear foundations apart even when the buildings themselves were designed to resist shaking. Lifelines are vulnerable because they cross the moving ground. Water, gas, sewer, power, rail, and road networks cannot simply follow each block. Joints pull apart, piles bend, bridge approaches settle, and quay walls move toward the water. A modest displacement distributed across a neighborhood can create a large systems failure. In 1906 San Francisco, lateral spread damage to water mains hindered firefighting. Secondary ground movement attacked the network needed for response. Flow failures are a more extreme branch. Under suitable loose material and slope conditions, liquefied soil or intact blocks riding on it can move far and fast. But not every liquefied site becomes a flow slide. Geometry, residual strength, drainage, and confinement decide whether deformation is arrested or runs away. The sequence now exceeds a soil column: shaking, pressure, weakness, displacement, utility breaks, and amplified emergency. Local physics creates non-local consequences through connected systems. On June 16, 1964, a magnitude 7.5 earthquake struck near Niigata, Japan. The city stood on young deltaic and coastal sediments with shallow groundwater. Strong shaking triggered widespread liquefaction. The photographs that became iconic show apartment buildings leaning at extraordinary angles, while much of their reinforced concrete superstructure remained recognizable. Those buildings did not need to shatter to fail. The soil beneath their shallow foundations lost bearing resistance and deformed unevenly. Some structures settled and rotated as intact units. The visual result looks as if a rigid model building was placed on a soft surface, because at the foundation scale that is close to what happened. The important geometry was a susceptible saturated layer extending from near the surface to a depth comparable with the building width. The foundation load needed a strong soil volume beneath it. When effective stress collapsed through enough of that volume, the load path spread, settlements grew, and rotation followed small differences from one side to the other. Niigata also damaged bridges, roads, buried structures, and ports. Each asset sampled a different depth and failure mode in the disturbed ground. Some tilted apartment buildings were later jacked upright, underpinned with piles, and reused. That fact is almost as revealing as the failure. The concrete frame had not transformed into liquid. The support conditions had changed. Repair worked by creating a new load path to material able to carry the structure reliably. Niigata made an invisible threshold visible. Its lesson is specific. Young saturated sediment, shaking history, and foundation geometry can make the ground fail before the building frame. In 1989, Loma Prieta damaged San Francisco's Marina District, including fill over former lagoon and shoreline environments. USGS found liquefaction and amplified shaking. Buried land history explained what the street map could not. Fill is not automatically dangerous. Placement, compaction, age, and groundwater matter. Loose saturated fill can still assemble all three ingredients. Christchurch, New Zealand, exposed the same systems problem at city scale in 2010 and 2011. Repeated earthquakes triggered widespread liquefaction in susceptible alluvial deposits. Streets filled with ejected sediment, foundations settled, and buried infrastructure failed. Multiple events also showed that prior shaking can alter ground conditions and complicate recovery. Zoom out and the pattern follows depositional systems. Abandoned river channels, point bars, flood basins, deltas, beaches, estuaries, and reclaimed edges. Zoom in and the pattern becomes layered and irregular. A regional map can identify likely zones, but site conditions can change abruptly over the width of a building. Groundwater is a moving part of the map. Seasonal variation can raise or lower saturation. Pumping, drainage, land subsidence, and coastal water levels can change the hydraulic boundary. USGS scenario work around San Francisco Bay has examined how higher sea level could increase liquefaction intensity at some natural soil sites by raising groundwater. The city therefore has two maps. One shows streets, parcels, and buildings. The other shows sediment age, buried channels, fill history, water table depth, and expected shaking. Liquefaction risk appears where those maps overlap with exposure. The hazard is not hidden because it is unknowable. It is hidden because the decisive architecture is underground. To test that architecture, engineers push instruments into the ground. A cone penetration test drives a standardized cone downward while measuring tip resistance and sleeve friction, often with pore pressure as well. The trace changes with depth, revealing stronger and weaker layers at a resolution that a surface photograph cannot provide. The standard penetration test samples resistance differently by counting hammer blows needed to drive a sampler. Shear wave velocity offers another view of stiffness. Borings recover material for classification. Groundwater measurements define saturation and hydraulic conditions. No single test is the soil's complete identity. The site model comes from combining them. Assessment then compares demand with resistance. Earthquake ground motion estimates provide cyclic stress demand. Field correlations built from sites that did and did not liquefy provide empirical resistance. A factor of safety or probability expresses the comparison. The calculation is powerful precisely because it carries uncertainty rather than pretending every layer has a deterministic switch. Case histories are the method's memory. Each earthquake tests the boundary using field resistance, groundwater, soil type, shaking, failures, and surviving sites. Regional models work at another scale. USGS ground failure products combine shake map motion with proxies for susceptibility to estimate where liquefaction effects are likely after significant earthquakes. These products guide awareness and response. They do not replace borings, field reconnaissance, or site-specific engineering design. The workflow moves from map to mechanism, zone, layers, groundwater, shaking demand, pressure ratio, and structural deformation. The result is a forecast tied to a structure and scenario, not abstract safe ground. Mitigation begins by choosing which link to change. Increase soil density so the grains are less contractive. Give pore water shorter drainage paths. Cement or mix the soil into a stronger mass. Carry structural loads through the susceptible layer with deep foundations. Reduce the load, relocate the asset, or design utilities to tolerate displacement. Densification rearranges loose soil before an earthquake, creating a tighter buried fabric that generates less damaging pressure and deformation under cyclic loading. Drainage methods add permeable paths that let pressure dissipate. Stone columns can combine drainage with reinforcement and densification, depending on design. Their value is a race against the shaking clock. If excess water pressure can escape fast enough, effective stress does not fall as far or remain low as long. Deep mixing takes a different approach. Soil is blended with cementitious binder to form columns or grids. FHWA guidance describes lattice arrangements that contain liquefiable soil and increase mass shear strength. Instead of asking loose grains to carry the same load more effectively, the treatment builds a new structural skeleton through the ground. Deep piles can bypass weak layers and transfer building loads to stronger material, but the design still has to consider lateral spreading, downdrag from settlement, bending demands, and the behavior of pile caps and utilities. Saving the vertical load path does not automatically protect every connection crossing the moving ground. Good mitigation connects shaking, soil, water, failure mode, structure, and acceptable consequence. It succeeds by breaking the specific chain that would turn a pressure threshold into unacceptable loss. Start again at the grain scale. Loose particles sit in a saturated layer. The earthquake applies repeated shear. The skeleton tries to contract faster than water can drain. Pore pressure rises. Effective stress falls. Contact forces weaken. From that one transfer, the possible outcomes branch into settlement, uplift, bearing failure, sand boils, lateral spreading, and flow. Liquefaction is not universal. The right question is which susceptible layer, under which shaking and structural load, produces which branch of failure. The ground also has memory. Depositional history sets grain size and density. Old shorelines and channels set geometry. Construction adds fill and foundations. Groundwater moves. Earlier earthquakes densify some zones and damage others. Engineering treatment rewrites selected links. What looks like a static parcel is a state assembled over time. That is why the most useful picture is not a building standing on blue liquid. It is a layered network. Fault motion becomes waves. Waves become cyclic stress. Stress changes pore pressure. Pressure changes contact force. Contact force changes deformation. Deformation crosses roads, pipes, foundations, and emergency systems. In the cold open street, the water at the surface was the last messenger. The decisive event happened earlier, when a hidden grain network stopped carrying its usual share of the load. The sidewalk waved because the solid beneath it had always depended on moving water, fragile contacts, and enough time for pressure to escape. Solid ground is real, but conditional. Change the conditions quickly, and the same grains behave differently. Liquefaction reveals that solidity is not an ingredient, it is a maintained state.